Hi everyone, welcome back to Chem Story. Today we're going to look at how alkynes react with halogens like chlorine or bromine. It's a pretty handy reaction, especially if you want to convert a triple bond into something more saturated, like a dihalide or even a tetrahalide. We'll take a look at what happens when a halogen molecule, Cl2 or Br2, adds across the triple bond. Then we'll break down the mechanism step by step and see how the products change depending on how much halogen we use. Alright, let's jump in. Alright, here's the basic idea. When you add a halogen, like Cl2 or Br2, to an alkyne, it reacts kind of like it does with alkenes, but this time, it happens in two steps. The first equivalent of halogen adds across the triple bond and gives you a dihalide. If you add another equivalent, that second one adds too, and now you've got a tetrahalide. Now here's something important. That first addition usually gives you a transdihalide, and the reason for that has to do with the mechanism, which we'll get into next. And if you keep adding halogen, you can fully saturate the molecule. Let's walk through the mechanism of halogenation and break it down step by step. In step 1, the pi electrons from the alkyne attack the halogen molecule, let's say Cl2, and that forms a bridged halonium ion. Then in step 2, a chloride ion, Cl-, comes in from the opposite side. That backside attack opens up the ring and gives us a transdihalide as the product. Alright, now let's zoom in and see exactly how the electrons move in this step. Here's what's actually going on in that first step. The alkyne has two pi bonds, and one of them donates electrons to the halogen molecule, Cl2. As that happens, the Cl-Cl bond breaks apart, and one chlorine leaves with a full negative charge. Meanwhile, the other chlorine forms a three-membered ring by bonding to both carbons of the alkyne, and that gives us the bridged halonium ion. Then comes the next move. The chloride ion, Cl-, swings in from the backside and attacks one of the carbons in the ring. That attack opens up the ring and gives you a trans-dihaloalkene, with the two halogens landing on opposite sides of the double bond. And that kind of anti-addition, it's a classic feature of halogenation. Now, what if you throw in another equivalent of halogen? In steps 3 and 4, that second Cl2 reacts just like it would with any regular alkene. You get the same two steps all over again. First, a halonium ion forms, and then a backside attack follows. So what do you end up with? You go from a transalkene to a fully saturated tetrahalide, with two halogen atoms on each of the original alkyne carbons. Mechanistically, it's the same story. The double bond in the trans-dihaloalkene attacks another Cl2 molecule, and once again, you get a bridged halonium ion. One chlorine bonds to both carbons, forming the ring, while the other breaks off as a chloride ion. Then, just like before, that Cl- comes in from the backside and attacks one of the carbons, opening up the ring. And that gives you the final product, a tetrahalogenated compound with 4 halogen atoms in total. There are a few different mechanisms that have been proposed to explain how alkynes react with halogens, including the one we already looked at in detail. So now, let's go over each of these possibilities and see what kind of evidence supports them. We'll start with the one that's most widely accepted, the mechanism that goes through a bridged halonium ion. This pathway forms a three-membered ring intermediate, just like we saw earlier with alkenes. It lines up perfectly with anti-addition, which explains why we mostly see transdihalides as the major product. And because it fits so well with what we observe, most chemists consider this the main pathway. Here's a simple example that follows that exact same pathway. As you can see, the reaction goes through a bromonium ion intermediate, and the final product is the E isomer, or in other words, the transdihalide. That's exactly what we'd expect from anti-addition, and it gives even more support to the idea that the halonium ion mechanism is the main route for this reaction. Now let's take a look at another possible pathway. This one goes through a vinyl cation intermediate. In this case, the halogen still adds to one of the alkyne carbons, forming a new CX bond. So that part's the same as before. But here's the key difference. Instead of forming a halonium ring, the other carbon is left as a free vinyl cation. This kind of intermediate is pretty unstable and high in energy, so overall this pathway isn't very favorable. Still, it's something to keep in mind, especially when we look at the actual product mixture. So why should we care about this mechanism? Well, even though the main product is usually the trans dihalide, or E isomer, we sometimes see a small amount of the Z isomer too. And the vinyl cation pathway is really the only one that can explain that. Since the carbocation is flat, the halide ion can attack from either side, which means both E and Z products are possible. So even if this isn't the main route, it could still be playing a minor role, and that alone is enough to account for the small amount of cis isomer we see. There's one more mechanism we should talk about, and that's the ADE3 mechanism, also known as the concerted pathway. In this case, the addition happens all at once, in a single concerted step, so there's no separate intermediate, like a halonium ion or a vinyl cation. Instead, both halogen atoms are added to the alkyne at the same time, through a single transition state. This idea mainly comes from theoretical studies, especially ones that focus on reaction kinetics. It's still a bit controversial. It hasn't been directly proven in experiments, but it might help explain some of the stereochemical patterns we see in certain reactions. Here's a quick look at what that might actually look like. As you can see, the two Br atoms are added at the same time through a three-body transition state. There's no charged intermediate in between. The whole thing happens in one smooth, concerted motion. The final product is still a trans dihalide, which fits with anti-addition. But the way you get there is totally different from the halonium ion route. So even though this mechanism isn't the most widely accepted, it's an interesting alternative, especially for reactions that happen really fast or in solvent-sensitive conditions. All right, to sum it up, alkynes react with halogens to give trans dihalides, mainly through anti-addition, and the halonium ion pathway explains that best. But we also explored two other possibilities, the vinyl cation mechanism and the concerted ADE3 pathway, which help explain a few of the exceptions we sometimes see. Thanks for watching, and as always, I'll see you in the next Chem Story video.